In example 1, you have a reaction, an arbitrary reaction, where you've got reactants in the form of A, B, and then you have products in the form of C and D. So this is a reversible reaction. There's a forward reaction and a reverse reaction. So this reaction takes place in a closed system. It takes place in a closed system. So a closed system means that the reactants and products, so reactants and products don't interact with the environment. So the reaction is in a closed system, meaning that the reactants and products do not interact with the environment. So now let's assess the question. So initially in the system there were 2 moles of A and 1 mole of B that were injected in a closed container of 2 cubic decimeters. Ignore this negative here, it's not supposed to be here. So they were injected, or they were thrown or put into a closed container that has got a volume of 2 cubic decimeters. And then at equilibrium, it was found that there was 0.8 mole of D left. So it was found that there was 0.8 of D left. Then calculate the equilibrium constant value. So that's the case here. Now, the first step that you do in this is you draw a table. We solve this using a table. And the first thing you do is, in order to draw the table properly, I'm going to write this reaction. I'm going to rewrite this reaction. There you have this plus 4D. So what we notice from this reaction is that it's a balanced chemical equation. So it's a balanced chemical equation. So we don't have to worry about balancing it, and it's an arbitrary, so it's a hypothetical chemical reaction because we don't have any element or molecule called A, B, C on the periodic table. So these are just arbitrary, this hypothetical. They're not real, it's just imagined, so don't worry about them. So you've got a ratio. The stoichiometric ratio is 1 of A and 2 of B, and then you've got 1 of C and 4 moles of D. So what you do is the molar ratio. When you draw the table, you make sure that each and every reactant and each and every product has got its own column. So this one we can make it big, it's fine, doesn't matter. And this one also will have its own column. So at the end of the day, including the name of the rows, we will have 1, 2, 3, 4, 5 column. So yes, 5 column. So we'll have this column, we'll have this column, we'll have this column and this column, and then we'll have the 5th one here, which indicates the name of the rows. Now the first column is going to show us the mole ratio. It's going to show us the mole ratio. So the mole ratio is, you've got 1 mole of A that reacts with 2 moles of B to give you 1 mole of C and 4 moles of D. Now the second row here is the row that shows you the initial mole. It's the row that shows you the initial mole. So the initial mole, So let's go back to our statement. Initially, so look at this weight, we're going to underscore it. Initially in the system there were 2 moles of A, 2 moles of A. So let's look at A, 2 moles of A. We put 2 here because there were 2 moles of A and 1 mole of B in a closed container, right? So it means that they didn't tell us anything about the product, which means that you didn't have any of the products. You had nothing. You had 0 of C and 0 of D because you were just starting the reaction, so you didn't have anything. And now the second row of the table that you need to figure out is the mole reacted and or produced. So this means that for the products it will be the moles that were formed, and for the reactants it will be the moles that reacted. So we don't know that. We don't know what those moles are. We don't know what the moles are. Right? We don't know what the moles are. So we're gonna take this thing here so that we just have some space here. I'm gonna add another row here and probably have the last one here. That drawing is very horrible. As long as you can see, that should be okay. We're gonna have 2 more rows. Anyway, that's okay. So you'll have the moles that reacted, but we don't know what those moles are, and we'll come back to that. And we'll have the moles at equilibrium. We'll have the moles at equilibrium. Moles at equilibrium, right? So this will be the number of moles at equilibrium. So what do we know? We know that at equilibrium, it was found that there was 0.8 mole of D left. So there was 0.8 moles of D left, right? And what we know is that if you started with 0 and then you ended up with 0.8, it means that you added 0.8, right? We don't know what is the moles of equilibrium at C. We also don't know what the moles at equilibrium are for B and A. So we have to find them. Let me just do this and create some space. Jeez. I'll go back to return that. Anyway, I don't know. Let's just leave it. It's going to create issues for us. So you created 0.8 moles because you didn't have anything in the beginning of the reaction, but you ended up with 0.8 at equilibrium. So it means that you added, or you created, or you formed, or you produced the 0.8 moles of D. Now, this row here, it's a very important row in a sense that it tells us the moles that have reacted and the moles that have been formed. So we can use it. We can use it to estimate. We can use it to estimate the moles that. We can use it to estimate the moles that have been formed for C and the moles that have reacted for B and A. So how do we do that? We use the molar ratios. We use the stoichiometric molar ratios. So let's look at the ratio of C and so the ratio of C and D is 1:4, right? So for every one mole of C that was formed, 4 moles of D were formed. So if 0.8 moles of D were formed, what would be the moles of C that were formed? And we can find that. So we do the cross multiplication and we have 4x is equal to 0.8 times 1 is 0.8, and then x is equal to 0.8 divided by 4 is 0.2. 0.8 divided by 4 is 0.2. So the moles therefore of C that were formed are 0.2. So 0.2 of moles were formed. So we put a plus here because this is what we added. So if you add 0 and 0.2, and you'll end up with 0.2. So at equilibrium, you'll have 0.2. And then you go to the moles reacted or the moles produced. So you use the same thing. You use the same stoichiometric molar ratios to find the moles of B and A that have reacted. And to do that, you're going to say, let's create some room here. You're going to say, maybe I'll use a different color, green maybe. You're going to say, for every 1 mole of A that reacts, there is 1 mole of C that is formed, right? So if 0.2 moles of C are formed, how much did you react of A? So you do a cross multiplication again. So 1 times X is X, 0.2 times 1 is 0.2. So what you can do here is that you can also use A and D. So it doesn't matter, you get the same answer. So here you'll have the number of moles being minus 0.2. Now somebody might be asking themselves, why does it become a negative? It becomes a negative because you are reacting, which means that you are reducing it in its quantity. So it's almost like you have a flour and some margarine and you're trying to make some bakes. You're trying to bake some cakes. If you bake cakes using flour and margarine, and you start with 1 kilogram and you start of flour and 1 gram of margarine, after some while, if you've made a couple of cakes, you would have reduced the amount, right? So you reduce that amount, you reduce the mass. So here you reduce the number of moles. When you react, they get used up. But in this case, they don't react completely. So, or even if they do, there's a reversible reaction. The products react again to form the reactants. So you have a forward reaction and reverse reaction happening simultaneously anyway. So now let's look at the number of moles that have reacted for B. So the interesting thing here is that you can come back and use what has reacted for A to find what will react for B, right? So, using the same thing, you could say 1 mole of A reacts to form 1 mole of C, right? So that's the ratio. Or you could say 1 mole of A will react with, according to the ratio, will react with 2 moles of B, right? So then what happens if 0.2 moles react? How much moles of X will react? You do the cross multiplication again. So 1 times X is X, 2 times 0.2 is 0.4. So 0.4 will react. So we put a minus because it is a reactant. Here we put a plus because it is a product. So now you have to find the equilibrium number of moles for your reactants, A and B. So now you started with 2, you react this, then you are left with 2 minus 0.2, which is equal to 1.8. And here you started with 1, then you react this, you are left with 1 minus 0.4 is equal to 0.6. So the equilibrium number of moles for A will be 1.8, and for B will be 0.6, for C will be 0.2, for D will be 0.8. Now the last thing you do here is you calculate the concentration. So the formula for concentration is the number of moles over the volume given. So this will be the number of moles at equilibrium over the volume that the reaction is taking place in. So So this will be 1.8 as the most divided by 2, which will give you 0.9. And here you'll have 0.6 divided by 2, which will give you 0.3. And here you'll have 0.2 divided by 2, which will give you 0.1. And here you'll have 0.8 divided by 2, which will give you 0.4. So this will be your molar concentrations at equilibrium for each chemical species here. So for A as a reactant, you'll have 0.9. For B as a reactant, you'll have 0.3. For C and D, etc., etc. So you're not done. So now you've calculated the concentration. You've calculated the concentration of your reactants and products at equilibrium. Now let's look at what you're really looking for is the Kc, the chemical. So the Kc expression for this reaction will be products divided by reactants. The concentration of products divided by the concentration of reactants. Now if you go and look at the reaction that we're given here, you'll notice that our products are C and D. So the square bracket represents the concentration. The square bracket represents the concentration, and we have to put an exponent value here. The exponent is 1 because the coefficient of the stoichiometry here is 1. The stoichiometric coefficient is 1, therefore the exponent will be 1. So we don't write it because 1 is an invisible number. And we have D. So the concentration of D, the exponent here will be 4 because the coefficient of stoichiometry is 4. Divide by the the concentration of A, the exponent will be 1, and the concentration of B, the exponent will be 2. So we know these concentrations at equilibrium. We've calculated them in the last row in our table. We can then say that we can just substitute the values. For C, we know that C is 0.1. Actually, now when you write them, you don't have to write the square bracket. I'm being very, very slow here because I want you to get this. I want you to understand this. So this is for C is 0.1, for D is 0.4, 0.4 to the exponent 4, and for A it's 0.9 and 0.3 squared. 0.3 squared. So if you punch the calculator, this should give you 0.0711. So this becomes your Kc value. So this becomes your Kc value. Okay, so that's it.